All right, we're in. Take it away.
Well, welcome everyone. Thank you for joining this month's EPSP Connects talk. So the purpose is to bring different researchers together from around the world. So we have a talk every month, and I would like to thank everyone that's involved in the EPSP Connects to keep this running and keep this organizing every month. So this time Roberto Fernandez is joining me as a co-host, so he will also be keeping track of like the chat and anything with like connections, etc., and meeting people. So anytime during the chat, during the talk, if you have any questions, just type them in the chat and we will monitor them at the end. But let me first introduce our speakers. Our speaker today is Dr. Lisa Luzzari, and she was talking to us about ice-covered rivers and mainly focusing on work on Finland, because she's been working for many years in Finland on research on all aspects of ice-covered rivers. That includes their monitoring, modeling, and also expanding to physical experiments. So she has a quite wide background in this, so it'd be very interesting to hear what she's talking about it. And she's also been a PI of several projects, and one that's now highly linked with the Digital Waters flagship. So without further ado, I will give the option over to Elisa to give the talk.
Thank you, Marika, and also thanks to Roberta for organizing this event and inviting me here to talk. As you see on the screen, I'll be talking more about this evolution and material transport of these seasonally frozen rivers. And I'm physically at Aalto University in Finland, which is in the capital region, so close to Helsinki. So my study sites have been exactly 20 years here in Finland. So I'm concentrating one of my main study sites where you hear the most, but I'll give first an overview of this topic and why this topic is, in my opinion, important. So as a background, as you might know, that more than half of the Earth's rivers are covered by ice during the winters. So there is seasonal ice cover in many of the rivers in the world. But then the climatic change is expected to impact the fastest, especially on the polar region, and where these river functions are quite dependent on the seasonal hydrology and the length of the winter season. So if it's ice covered or open channel flow period. So how these rivers are then changing due to these hydrological and climatological changes is a big question. So especially the rivers in Finland, Sweden, and Norway, which are in this region, are crucial study sites for understanding these environmental changes to these fluvial systems, and so that we are able to enhance the adaptations to the climatic change. But there is actually quite big gap still in the knowledge how this relationship between the river ice flow characteristics and sediment transport are interconnected in different river types and in different seasons. So overall, the aim in my current research, which covers multiple different projects, as Marika just said, its aim is to create these new space-time theories of these interacting river ice flow characteristics and sediment transport under these changing environmental conditions. So I'm using these measurements, experiments, and also modeling as the tools for getting some results out of the river systems and how they are changing. On the right-hand side, you can see a picture of the rivers which are north of 60 degrees, and then also within the Arctic Circle. So many of the rivers, or basically all of the rivers in Finland, are covered within this region. Some of them are flowing to the Arctic Sea and some of them to the Baltic Sea. So the P sign, which is there marking the Pulmankijoki River, is one of the main signs I'm talking today and giving most of the examples, as I can't cover all of the rivers in one talk. But here you can get this kind of idea, what is the context of this region, what we are talking about. And I want to mention here also the Digital Waters flagship, because even though the overall aim in my multiple projects are within these kind of new space-time theories and these ice-covered rivers, there's also highly important that these technological advancements are developed at the same time. And we have this really new consortium in Finland, which covers multiple different partners, and the leaders are from University of Oulu and University of Turku, and Aalto University is one of the partners. We have also the Finnish Environment Institute, Land Survey of Finland, and the Finnish Meteorological Institute involved. So the idea is that we have in this Digital Waters flagship new technologies, making these digital twins from different watersheds so that we can understand these seasonal processes also better. So this is one big driving force on the background at the moment. So if you are interested on this flagship and also collaborating with us, please go and check these web pages of digitalwaters.fi. But so the aim is that we will get this improved water security also when we know more about these river systems, their changes and fluvial processes at present, but also in the future with these enhanced methods. So actually my presentation also involves quite a lot of different technical novelties, which could be then applied also to other study sites than the ones we are talking today. Here you can see this overall larger consortium study sites in Finland. We have from south Vantajoki, Aurajoki, and then in a more north Oulankajoki. And then the northest one is the Tana River, including the Pulmankijoki River, which is the specific site I'm talking today more in detail. So we are hoping to get these digitalize these watersheds, digital twins out of them, and then also this enhancing the process understanding from different seasons at the same time. Here is a short video what kind of measurements we have been doing from these study sites in a previous years so that we can understand the hydrosphere processes, the channel changes, and then what kind of measurements have been needed and what will be done. So here are the glimpses of different sites at ice-covered conditions. And you can see some of them are really shallow and the ice is really thick, but there's also material transport underneath the ice quite a bit. Then also the spring season is important as there is this ice breakup and then also this flood situation which followed by then. Different methods include laser scanning, remote sensing, flow measurements, ground penetrating radar, and all different kind of drone measurements of for being able to get these topographical data and also flow data sets. So I'll show about more about these methods and outcomes in the next slides. Oh, now it starts again. But why I started to study about these ice-covered rivers. So I had my PhD defense in 2012, and during the time I was working on these climate change impacts on the flooding and sediment transport in Finland, but noticed that there is little studies done from these ice-covered conditions. So, but then I gathered how many of these models or future simulations actually had sediment transport included in the models at that time. As a result, you can see on the right-hand side that it was quite small amount of studies which had included actually the sediment transport in the models. And basically, they were doing the modeling from the open channel conditions. So there is actually a lack of observations and calibration data and models capable of doing these ice-covered sediment transport simulations in these northern river systems. So in this postdoc project started to do in 2014 winter with the collaborators from Finland also, these systematic under ice measurements at this Pulmankijoki River. So that is why I'm also talking about this Pulmankijoki River in northern Finland mostly today. So we have been gathering the data sets for understanding these ice-covered processes for around 10 years in this specific study site, but there is more still to be understood. This is one of these earlier papers of ours with collaborators showing how the seasons are expected to change. So this white rectangle is showing that the spring flood or the expected highest flood would happen on other seasons than in the spring, when the snowmelt flooding is currently the biggest flood time. So in the future, 2070 to 99, it's expected that the highest flooding would change to be on some other season than in the springtime, which also then shows that there's something happening in the future for the winter period. Very recently, together with these collaborators from Finnish Environment Institute and PhD student of mine, Ture Takala, been calculating this, how the accumulated freezing degree days would be changing in this Pullmankijoki region in the near future and until the end of the century. So you can see on these gray box plots that the length of this winter period, when these temperatures of air are below the zero, will be shortened. And this impacts directly to the ice-covered season, and then also how the water is flowing into rivers and impacting on the erosion. What is then also recently known or seen from these rivers from Finland, Sweden, and Norway, which we are at the moment detecting. And actually, I'm giving a presentation in the AGU more about this in a couple of weeks' time in Vienna in a conference, that there is actually quite many of supercooling events, which means that the temperature goes below the zero due to the drastic changes in air temperature below and above zero. And it has been forecasted in Finland and also in these other countries at these same latitudes. There would be more and more about these zero crossings of air temperature, which then means that there is fragile ice also in the river. So the red dots on both of the figures are showing the timing when there was, for example, in Pullmankijoki River, fragile ice in late autumn 23. So there's quite a many of occasions, and it's expected that that would be increasing, and that would also impact on the river erosion, and then also these freezing conditions, which are impacting on the flow of the channel. So this is something that is ongoing and needs to be detected even more, because these are the behind affecting factors for the evolution of the rivers in these latitudes. So as an example, also another study which is ongoing, we were actually lucky. We were in 21 autumn during a period where these supercooling events and also the fragile ice, which you can see on the middle or below in the screen, are floating in the channel. But then we noticed also that there is bottom fast ice, which you can see behind or on the background there underwater. And it was growing fast during these 4 days what we were measuring in this river. And on the right-hand side, I have actually just manually digitized how this bottom fast ice was taking place within a short reach of this Pullmankijoki River. So it's covering quite a lot of this river channel, affecting on the flow conditions and then also affecting on the sediment transport of these rivers. So this is one part which needs to be understood before we can actually simulate these river channel developments to the future in these latitudes. And along with the climatic change, these fragile ice development in the riverbed and floating are expected to increase in the timing. But how do we then analyze these? For example, there's recently these image velocimetry methods, which can be used to getting these surface flow velocities from different rivers. Here is an example from one of my PhD students' work just published from one of these restored study sites. But this is just as an example that with this method, when you are flying with the drone, taking a video from the river channel, you can convert it to flow velocities of the surface. So this exactly same method can be used for getting this understanding of these flow velocities, shear forces during also these fragile ice periods and how these are impacting then on the river channel evolution. You can also use these surface flow velocity datasets as a enhancement of these numerical model approaches. Here is another study recently published with my colleagues from University of Eastern Finland and University of Dresden from Germany, that you can convert these surface flow velocities and as mean flow velocities of these reverse channels from different time periods if you are doing these measurements seasonally in freezing or thawing conditions or also in open channel conditions. And you can use these as a calibration of the models to make them function better or giving the results more corresponding to the natural system than before. So you can enhance the spatial understanding of the flow conditions and then also the sediment transport conditions when you calibrate the models even better. We have also these new camera systems by the riversides in different sites in Finland, including this Pulmankijoki River. So if you have these thermal cameras, RGB cameras, or multispectral cameras, you can get this video data set out of them, and then also convert or analyze similarly the flow velocities, especially from RGB cameras and the thermal camera videos as you would do it from the drone data sets. So based on that, you can get these temporally really dense flow velocity data sets. For example, we have been measuring these videos every 2 hours from these different rivers we have. And here is also a recent publication that you could analyze. On the right-hand side, you can see how the red parts are the flow velocities, and then the blue dots or the boxes are the ice cover. So when ice cover increases, the flow velocities are decreasing. And you can actually see this interaction between flow velocities and ice cover development much better and more densely than if being needed to measure at the river during this quite difficult measurement time, which is the ice development and ice breakup periods also in the spring. So why I'm talking about these flow velocities is because it's very important for all the sediment transport and how these morphological changes are taking place in the river channels. And when you have more and more about these reference data sets from different sites, for example, from these basic time-lapse camera systems, which take videos, you can get these calibration data sets for the models even more and more and temporally more densely. We have also been doing these ice-covered flow measurements and also the sediment transport under ice and trying to understand how then the mid-winter ice conditions are affecting on the sediment transport. Here is just a picture from a recent paper where we did measurements in one meander bend in this Pulmankijoki River. So there is this these different maximum near bed velocity locations from different years what we had there. So although the ice-covered flow is less than in open channel conditions, the flow velocities were able to transport the material even in these midwinter conditions when the ice thickness can be from 30 to 70 centimeters in these reaches. So it has been actually taking quite some time to state that there is actually sediment transport in these seasons, which can, for example, in Pulmanki River, be 7 months a year from October until the end of April. So that's a huge part of the year which is covered by ice. But in the future, it's expected that these seasons are shortening, these ice-covered conditions. So before we are able to understand what will happen in these possibly shortened ice-covered periods, we also need to know what is currently happening in the ice, underneath the ice, so that we know the amounts of sediment that are then transported to the Arctic seas, for example. And please note that this Pulmankijoki River is quite a small river, so it's 20 meters in width, which is easy to handle in these kind of measurements. But if you go to these larger rivers in Arctic Canada, USA, and then also in Siberia, for example, the sizes of the rivers are even more enormous. And you can imagine that if in this small river, the flow velocities are able to transport the sediment under ice, there is a huge unknown factor also in these Arctic rivers, how much there is happening under ice-covered conditions at present and in the future. But hopefully these examples from this one site and the methodological development here and also elsewhere in the world could give more understanding of these sediment transport conditions there to the northern seas. So for example, also it's expected that the ice cover impacts on the flow velocities, the circulation of the flow within the meander bends, within rivers, making the high velocity course closer to riverbed, changing the circulation of the sideways circulations or these helical flows of this water under ice. And also if the ice cover is really thick, then the flow system changes even more. So it's important that these changes in flow characteristics are detected in midwinter conditions, which we have done so far with the colleagues of ours for 10 years now in Finland. But then recently also we've been starting to do even more quantification for this bed load transport or sediment transport under ice. So here is a really short glimpse of really novel work of one of my PhD students and us. So this is unpublished data set yet. So we've been doing this measurement with the GoPro videos underneath the ice, making this ADCP flow velocity analysis at the same time, and also getting the bottom track velocity out of these ADCP acoustic Doppler current profiler. And then we also have the bathymetry data from the ice-covered conditions. So with these video data sets of the GoPro, similarly as you can detect the surface flow velocities from the rivers, and then also this ice rafting and getting the knowledge of these fossilized conditions, you can get the understanding of this riverbed motion from these videos underneath the ice. We've been comparing this to this mechanical sampler, the Hello Smith sampler, which is highly used, and shown that the mechanical sampler actually has quite big errors, as you probably everybody knows that there's uncertainties in these. But here is a short, these are yet unpublished, so sorry for that, but hopefully soon to be submitted in some of the journal. But here you can see one of the measurement on the left-hand side. It's a 6-minute long video, and this Juha-Matti Välimäki gave permission to show it here, these unpublished results yet. So if you follow these 6 grids on the left-hand side, first is from 0 to 60 seconds, then next is 60 to 120 seconds, and so on. So it's all in all a 360 seconds long video. From all of these 6 panels on the left-hand side, you can see that there is this edge of this dune moving. I don't know if you see the cursor on the screen or not, but you can...
We can see it.
Okay, good. So from here, you can see that it's along this line, but after 6 minutes, it has already moved quite much up forward. So it's moving this edge of this bar formation, even within the 6 minutes, quite a lot with this sediment transport, what is happening there. So from these video data sets, you can actually see when you convert these particle tracking to bed load velocities with these novel different methods, which hopefully will be published later on, and you can read more about this methodological part. You can actually get these bed load transport rates much more in detail than with these mechanical samplers. And this is especially crucial for getting these simulations underneath the ice even better and better calibrated, and then hopefully getting understanding of these future changes in these northern river systems. So there's a recent publication also from our team here at Aalto University that we tried this sediment transport simulation under ice conditions with a simple HECRAS model. And that time we used mostly about these Hello Smith mechanical samples. Even with that one, it was possible to show that the models are somehow able to simulate the sediment transport, but the importance of this good quality data to calibrate the models was even noticed more strongly, and these image-based estimates of the sediment transport could be proving these calibrations. But one important thing was that also the current transport function formulas used in these morphological modeling would require adjustment and quite a lot of calibration before they were able to represent the situations in these ice-covered conditions, as many of the equations have been developed in open channel conditions or in the flume system. So that's a big question also, how they are functioning in the ice-covered conditions, and hopefully being able to get more knowledge of that very soon in different papers what we are working on. Here also sorry, I know that there's a lot of information and data, so I'm happy to hear more questions and later on, but still continuing a bit to these under ice measurements, and then as the last part of this presentation about this bank erosion, what we have been noticing. But before going to this bank erosion, just wanted to say that there is also this underneath the ice for enhancing the modeling. In addition to the sediment transport, I think one of the big issues in this modeling has been how to define the roughness of this riverbed and also actually the river ice. So we've been recently doing with these under ice drone measurements, these underwater drones, having just GoPros or RGB cameras that are filming videos, that you can actually make the structure of motion or the ice underside elevation model, which of course it has a bit more inaccuracies than if you would do it from the land surface. But still you can get the roughness values out of these ice and be able to get then more these calibration parameters for these models for simulating the future changes in the river flow and then also sediment transport. So this is what we've been working on and getting these kind of parameters more in detail. And some of our team members are at the moment actually working on also understanding these ice-covered flow conditions and later on sediment transport more in detail, that we have been carving these on the middle, you can see the ice underside, which is actually now on top of here. So that's the roughness gotten from these underwater drone systems. And then on the right-hand side, you can see this riverbed topography, which is gained from also these under ice measurements. And those have been carved. So this is actually representing this Pulmankijoki River. And next steps are doing these experiments in the flume, getting more information of this, how these ice cover and riverbed are affecting on the flow velocities, and later on also on sediment transport, but in controlled flume experiments. And hopefully getting more information for these future simulations also, and model development. But then I have now gone a little bit of this autumn season, this freezing period, then the midwinter conditions, we have been measuring, and now going more to this riverbank erosion, which is especially taking place in the melting season or the spring snowmelt season what we have. Here is on a background bit late, like older publication of ours, me and our collaborators from University of Turku and Land Survey of Finland. Based on the laser scanning datasets, we have been measuring this Pulmankijoki River for years, and they are still continuing also these laser scanning measurements there. But what was shown in that on the right-hand side, you can see different meander bends of that river system, and especially this bend one, which is this one high bank, which is around 16 to 18 meters high. This bank system there, you can see there's differences between the years. So the erosion is the yellow or red, and green is the deposition. So actually the duration of the spring snowmelt, maximum water stage and related submergence was more important for the either aggregation or the erosion of these point bars and banks than the local effect of each of the meander bends. So it was similarities between these different meander bends in this river channel evolution in this river system. But what was possible to get out of this? So this is the bent one, which I'm concentrating now on in the later slides, also based on different studies, that there was differences what is causing then the erosion. In the middle picture, you can see that there was this one spot where was erosion and deposition during one of the years there. So that was actually a location where groundwater is seeping through the bank. Then there is different processes which are caused by the flowing water and mass movements, which were closer to this apex of this one meander bend and its bank. But there was also this erosion caused by rain and mass movements during these open channel flow periods. So there was actually different parts of the bank which were eroding due to different processes. And there was also differences between the seasons. So up here on the graph, you can see the impact of snowmelt discharge event on the erosion. So most frequent changes in the bank system happened during the peak flow, but actually the greatest magnitudes took place in the falling limb of this hydrograph. But then in the summer discharge events, which is also open channel flow conditions, there was most frequent changes in the rising limb of this hydrograph. So there's differences if it's in the spring snowmelt season, which is then more colder season also. So the water temperatures and the banks are still a bit more frozen during that time or before the flood starts, but then in the summer periods. But that's also a question like why is that and what's happening there, and if the climatic change is taking place or when it is taking place, and with different magnitudes, how it will be then causing this bank erosion in addition to actually the vertical changes underneath the water due to the flowing water. So these different methods have been also developed on this bank erosion analysis recently. So we have this from Pulmankijoki River, this one bank, which is around 16 to 18 meters high, which you can see on the picture. So it's actually quite high bank. And we have also had these game cameras or time-lapse cameras there for a few years to measure every 2 hours. And we have 4 cameras there, which are detecting the same location. So based on that one, you can build up these surface topographies out of the data sets or these different camera images which are synchronized taking at the same time. And then based on that, you can analyze the volumetric changes at each time step and then get the volumes, how much it's changing. So there is these negative changes and positive changes which have been recently, just this year, published from this riverside together with the German colleagues from TU Dresden. So there's actually these simple camera systems are quite important for many kind of different studies. So as a last, I want to also show what has been then tried to or done together with the collaborators from University of Hull in UK. And that we tried to or did these experiments in small Fritken type of flume, where we had so tiny banks as 2 centimeter heights, but we had the grain sizes and then the flow velocity similar to this observed at Pulmankijoki River. So basically we had references to this northern river system, but did these experiments in this kind of a cryolab environment where we could control the air temperature and then also the moisture content of these riverbanks and see how much these changes in the air temperature could affect on the erosion of these banks, and hopefully get some more understanding what is actually happening in these real life riverbanks or the behavior under different constraints of environmental changes. So this is also unpublished data yet, so please treat it as it like that so far still. So what has been noticed from this flume analysis that there is actually a nonlinear relationship between these erosion rates and the air temperature. And quite surprisingly, it was that the highest erosion was when the air temperature had been around minus 5.2 in these high discharge conditions what we used there. So we had 2 different discharge conditions, so higher and lower. So So then the erosion rates were a little bit less if it was below or above the -5.2, but then increased again at the +4.5 degrees. So that's so it did not go linearly with the temperature. Also, the high moisture content slowed the temperature propagation through the bank, and then also affected on the erosion. So the erosion occurred as blocks in these freezing conditions when the moisture content was exceeding 18.9%. So it had quite a lot of impact if there was enough water within the bank. For example, if there in a real situation there would be groundwater or high moisture contents which have been freezing to the bank. And then if the temperatures were around -5.2 or so, that it promoted this erosion of the bank faster. So the more I have been learning about this knowledge is that of this riverbank erosion that is really complex even in this kind of a tiny river system in northern Finland. But these, hopefully with these technical developments and just based on the glimpse from this one riverside, we can get some ideas of technical development, how we can enhance the measurement and modeling, and how these then behavior during different seasons, or how the behavior is during different seasons in this type of a sandy gravelly river. But then hopefully these methods and analysis could be also upscaled to different river systems in northern environments. So I think there are still many, many questions open. What will be happening in the future to these different river systems? But I think we are getting closer and closer there when the development of the methods to get the reference data, and then also these different modeling approaches are possible to do. So it's important that there is detected the spatial differences between these river systems, which have different material, slope, and watershed characteristics. And so this is work in progress, and me, my team at Aalto, and also the Digital Waters flagship are very much interested in on collaboration suggestions. So please feel free to contact me and collaborators with the low threshold. I know that I talk fast and a lot, and there was a lot of information. But thank you, Kiitos. And if you are interested in contacting me, there's the email address. And then also, if you are using, for example, Instagram, so take this our teams into your, or start following our team, so we can then also you can see then updates from our field measurements and studies in Finland. Thank you.
Thank you, Elisa, for a very interesting talk and a very broad overview of all the different work that's ongoing. I've not seen yet anyone post any questions to the chat, so feel free to do so. I don't know if anyone has any questions.
I can ask one to get started. When you mentioned the head-crust model, did you kind of go with like a single sediment transport equation and then you try to calibrate it somewhat, or you tested a few? How did you go about that?
Yeah, there was few equation tested, and yeah, there was these calibration coefficients within these sediment transport equations, and then compared to these actual Hello-Smith sediment transport amounts, and then we had also preliminary results out of these bed load measurements with these camera systems. So it was compared to those ones also. So yeah, so there was multiple different tested. And it was one of the postdoc of our team called Virpi Pajunen, who was the actual one who did the modeling. So I can also give her contact details if you want to know more in details about this model development there.
Do you happen to remember which one might have performed better by any chance?
I should have checked it now.
That's fine. We'll go find the paper when
yeah.
it's all out.
Yeah, there was Maya Peter Müller and Engelund Hansen at least used quite a lot. So I can also check it and send you the details later.
Thanks.
Yeah, thanks.
All right, we do have a question in the chat. Can you kindly explain the physics behind estimating the velocity from the videos, and what are the best tools available to do so?
Yeah, there's actually different methods, and we have been using this particle tracking velocimetry method, or this LSPIV large scale image velocimetry methods, for example, quite a lot, and Steve method, which is the space-time imagemetry velocimetry method, or image velocimetry method. So they are detecting these different frames from, so the videos are converted as different frames. And then based on the particles detected, for example, in the PTV method, it's compared how much it travels between these different frames, and then it's converted to these velocity values. So there's quite a lot of these different literature available, and our team has been developing or combining these different equations available from the different literatures of these methods, and then being able to develop this further, also with the collaborators from the TU Dresden. So basically all of these methods are using different frames, a little bit different calculations behind these different approaches. Either it's based on single particle, or if it's in a gridded format. So for example, the LSPIV has been between these different grid cells of the different frames of the videos detected. So as a short answer, but it's actually quite complex equations behind, and we can answer you more if you can give us an email, and especially the PhD student who is doing this bed load analysis development is an excellent person to also help in this if you're more interested.
Context can be set up. There is a follow-up question, or like a small follow-up. What is the accuracy of these methods?
Actually, the sensitivity analysis is ongoing at the moment. So hopefully within 2 weeks' time, we will have a little bit more of this accuracy, especially on these bed load analysis methods. But what I have been comparing these flow velocities, yeah, because we have also these flow velocities from acoustic Doppler velocimetry, and then also acoustic Doppler current profiler. Of course, there's a little bit of difference in the because the sensors underwater have to be below the water surface a little bit. But what we have been comparing is actually quite good match, or very good match. So it can be said that you can get the similar velocities from the surface as you would get from these acoustic basic velocimetry, acoustic equipment what you are normally using to get the velocities from the river. So we are quite happy of the results of this video method. But the actual accuracy numbers, I'll have to check more in detail in coming weeks.
All right, so we've got another common question. Thank you for the presentation. Do I understand correctly that there is no permafrost in the rivers you mentioned? I'll let you answer that, and then we'll continue, because it's got like 3 questions in a single from a single person.
Yeah, this Pulmankijoki River, it doesn't have permafrost next to the channel, but it has this kind of a sporadic permafrost within the watershed. So there is, for example, these balsa mires, which are mires where there's ice core, and then the mire or the bog is raised up due to that one, and there's collapses of the also of these balsa mire mounds, which are due to this environmental change and the lowering of the permafrost surface. But it's further upstream or further away actual this channel. So if concentrating now in Pullmonkey River on this river channel, so there's no permafrost immediately next to the channel. So no permafrost interaction.
Have you measured the soil temperature and taken it into account? Will the soil temperature and its freezing process during the winter affect intensities of riverbank erosion?
Yeah, we have measured soil temperature. So we have had these kind of, for example, hobo soil temperature sensors, and recently also soil scout sensors, which are sending online data set of the soil moisture, soil temperature, salinity, and then also motion. I didn't show these results in this presentation because I thought it might be a bit too long even then, this presentation. So we do have those data sets, and their detection is actually also ongoing. We have 2 published papers already about this method and how to detect, done by me and some of my team members here. So, sorry, what was the question? So, yeah, so it's under work, the analysis. But there is indeed differences between the winters what we have been measuring. So we will be able to get in one of the papers which is ongoing that there is differences in the riverbank motion and then the how much it has been frozen. But the work is still ongoing. But it's quite promising that we can get some connections. But sorry, again, I can't say much more in detail.
I have a little follow-up to that, Elisa. As you know, you go out there throughout different seasons, you know, the question here is alluding to, you know, if the bank kind of freezes, that might slow down erosion. But how about summer with vegetation potentially growing? Is that also something you see in this system? You know, so the bank might be controlled in the summer by vegetation and in the winter by ice, or, you know, yeah, permafrost, I guess.
Yeah, this specific Pullmonkeyjoki River and many actually rivers in Finland which are within this kind of meandering sandy gravelly rivers, because they are old sediments from the declassiation. So it's quite sorted sediments where these are flowing these rivers, these lowland rivers. So the banks are quite bare. So it's actually not so much of vegetation in this Pullmonkeyjoki River in all of the banks. But of course, in some lower banks or in some parts of the river, there is vegetation, which is then, of course, affecting on the erosion. But it has been seen that if there is taking place a mechanical ice breakup, also the vegetation is there, then torn off, and it's kind of there's a lot of interaction on those, but I'm not specialized on the vegetation, so more concentrating on sediment transport and these physical processes. So that's needed to be analyzed in a separate studies and by other colleagues of ours.
Thanks.
Is there some more?
Not at the moment, and it also means that we can finish on time. So thanks again for giving a very interesting talk and taking the time to make it and give it. The next speaker next month is Roeland van de Vijzel from Wageningen University. And I am not entirely sure personally yet what
we
he's
haven't
going to be talking
heard
about.
back on the specific topic, and I'm glad the Dutch person got to say who's the speaker next month, because I would have not pronounced it that way.
Maybe in pronouncing it the English way, people would have recognized the name better. But anyway, details will be shared in a normal way, so I'm sure everyone can find the details of the talk and the exact date and time and the topic,
thanks.
of course.
Thanks, everyone. We'll see you next month.
Thank you.